Hi everyone. Today let's talk about session 6.2, Permutations and Combinations. If R objects are chosen from a set of n distinct objects, any particular arrangement or order of these R objects is called a permutation. For example, 4, 1, 2, 3 is a permutation of the first 4 positive integers, and the other permutation, it could be 1, 2, 3, 4, 2, 3, 1, 4, etc. And I want to point it out that permutation, the order really matters. Okay, so the order matters. Okay, so let's look at some examples. A, how many ways can I arrange all of you in class? Okay, so what is the total number of permutation of students in the class? Okay, so the number of ways we can arrange n elements is n factorial. Because the order really matters, so we're looking at the number of orderings, okay? So let me see. Okay, so we want to arrange n objects, right? So it's like we have n boxes. Well, the first box, how many choices are there? Well, there are n choices, right? And then second box, how many choices left? So we already picked 1, so we have n minus 1 choice. And the next one, n minus 2, until we have 2 choices, and then we only left with 1 choices. So that's why the total number of ways we can arrange n elements is n factorial. So n factorial is n times n minus 1 times n minus 2. So we count down the numbers until we reach 1. So far, so good? Okay, so how many ways can I arrange 10 things? Well, the answer is 10 factorial. Okay, so what if we're arranging them in a circle? What is the number of ways we can arrange n objects? Well, we can think about it's like 2 steps. Okay, so step 1, we want to select 1, okay? So we want to select an element arbitrary, okay? So we say we select the 1, okay, first arbitrary. Okay, so we have a circle. So let's say we have n things we want to place. First, we want to select a position to place. Okay, so arbitrary. So we place it 1 here. Okay, and then we can select the rest. Okay, so then we can seat the remaining 9. Okay, so we can see the remaining line. Then we can, so we pick this one, sit down first, okay? And then for the remaining 9, now it becomes the tail. So it's like, oh, after we put this down here, then the remaining we can line them up, okay, into boxes. That's why so the number of way here now, okay, so the number of ways is 9 factorial. Because the 9 boxes, the first one we have 9 things. Why is 9 things? Because we already placed the number 1 into a spot. Okay, so and actually step 1, when we place the number 1 arbitrary and we don't count the numbers. Why is that? Because if the circle, okay, if we just pick 3 things, so 1, 2, so we put them in a circle 1, 2, 3. Okay, so this circle and the circle 1, 2, 3, and this circle 1, 2, 3, they're the same thing. We count it as the same the same numbering as a circle. Okay, so that's why even though step 1 we can have several pictures, but we consider they're the same arrangement. Okay, so it's step 1. So you can see the number of ways, only one way, because we can consider they are the same arrangement. Okay, no matter where we place it, that element, we can consider it's the same arrangement. So far, so good, everybody. So that's why if we arrange and items in a circle, okay, the number of ways we can arrange and objects in a circle is gonna be n minus 1 factorial. So far, so good, everybody? Yes. Okay, what if you want to find the number of arrangements of n items, but you only want to arrange r at a time? Okay, we want to arrange r at a time. So which means instead of arranging all the elements, we only have we want to pick r elements of them to arrange. Okay, so this is we have r boxes. Okay, the first one we have n choices. Second one we have n minus 1 choices. And then, okay, what is the last one? Okay, think about it. This is the first box. Second box, this is r box. And then for the second box, this is 2 and this is 1. So the last spot, this is r, then this should be r minus 1. So that's why here this is the same as r n minus 1 dot 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 until we get n minus r plus 1. So far so good. So let's see. Okay. Theorem. The number of permutations of r objects selected from a set of n objects with order matters is, this is permutation n choose r. Okay, that is n times n minus 1 times da 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 times n minus r plus 1, which is exactly we show it here. Okay, so we want to pick from n object, we want to pick r objects, and with the order matters to arrange. Okay. And what is this guy? Well, you can think about we can multiply the numerator and the denominator by n minus r to the factorial. Okay, so n minus r factorial. Now what happened? What happened to the numerator? The numerator, because it's n minus 1 plus 1, the next number when we count down is going to be n minus r. So the factorial will count down the remaining numbers until we reach 1. So that's why the numerator is just n factorial. So that's why we have n factorial over n minus r factorial. Okay. Alright, so this is permutation n choose r. Let's look at some examples. Part A. How many ways can you arrange 10 items if you are only choosing 3 at a time? Alright, so we only choose 3 at a time. So the first choice, we have the first item, we have 10 choices. Second item, we have 9 choices. The third item, we have 8 choices. So that equals 9 times 8, 72, 720. Okay, so this is in our notation, this is permutation 10 choose 3. Okay, so this is permutation 10 choose 3. So far so good. And how you calculate? You start with 10 and then you count down 3 numbers. Okay. And then part B, we are going to find how many ways we can assign the positions of president, treasurer, and secretary if you have a class with 30 students. Okay, so we have 3 positions. We have the president, treasurer, and the secretary. President, how many choices are there? 30 students. And then how many choice left for treasurer? Because we're choosing different students, so that's why we don't repeat. So there are only 29 choices left for the treasurer, and then for the secretary, there are 28 students left. Okay, now we can put this in our calculator. 30 times 29 times 28 equals 24360. Okay, so this is permutation 30 choose 3. So far so good, everybody. All right, let's continue part C. I have 6 unique math books, 5 unique programming books on my shelf at home. In how many ways can I arrange these books so no mathematics books can be adjacent to another mathematics books? Oh, okay. So here we have 6 math books and 5 programming books. We need the math books. They're not next to each other, so the math books are separated by the programming books. So the picture is gonna be we have math, programming, math, programming, math, programming, math, programming, math. How many math are there? 1, 2, 3, 4, 5. Oh, we need 2 more. Okay, so then now we have 1, 2, 3, 4, 5, 6 math books, 1, 2, 3, 4, 5 programming books. And because we have exactly 6 math books and 5 programming books, so this trend of math programming is already fixed. Well, if you have 6 math books and 6 programming books, then you might have some variation. Maybe you have 2 programming books together somewhere. Okay, but in this case, because we have 6 math books and 5 programming books, so this arrangement is already fixed. So now we only left to arrange the math books and arrange the programming books. Okay, so first we arrange the math books. Okay, and there are 6 spots. The first spot we have 6 choice. Second spot we have 5 choice. 4, 3, 2, 1. So that's 6 factorial for the math books. Okay, so far so good. All right, next. We're gonna arrange the programming books. Okay, so there are 5 spots. So 5, 4, 3, 2, 1. That's 5 factorial. Okay, and that's why we get the total number is 6 factorial times 5 factorial. And what is that? I know 5 factorial, okay, is, so 5, 4, 3, 2, 1, that's 120. 6 factorial is like 5 factorial times 6. So 6 times 120 is 720. 720 times 120. Okay, let's see. Put this in our calculator. 120 times 720. Okay, I get 86400. Okay, so this is part C. Alright, just save it. Okay, let's continue. Part D. How many permutations of the letters A, B, C, D, E, F contains the substrings of D, E, F? Okay, so we have how many permutations of letters? Okay, so we have 6 boxes, right? Okay, so first of all, we want to place the D. Okay, let's separate into steps. Step 1, place the D. Okay, where can I place the D? Well, I can place the D here, here, here. But can we also here? Can we place the D here? No, because you need to leave some space for the E and F. Okay, so let me see. Oh, okay. I just realized here I draw too many boxes. So we have 6 boxes. Okay, and we can place the D in the first 4 boxes. Okay, so and we cannot put it here. We need to leave this. I mean, we need to leave some space for E and F, right? So that's why we have 4 choices in this case. Okay, step 2. So after we place the D, then the E and F come after the D. Now we already fill in 3 letters. How many boxes left? We only left 3 boxes. Maybe they're not connected together, but we only live with 3 boxes. Okay, so the 3 boxes, okay, so here we want to place the A, B, C in the remaining 3 boxes. Those 3 boxes might not be connected, but it's okay. It's just whatever boxes is left after we fill in the D, E, F. Okay, maybe we fill in the D, E, F, like here, D, E, F, and then we only left with 3 unfilled boxes. Okay, so we can fill it with A, B, C. In the first boxes, we have 3 choices. Second boxes, 2 choices. Last one, 1 choices. So the total is 6 choices. That's why the total number is the number we get from step 1 times the number we get from step 2. 4 times 6 is 24. So far so good, everybody? Okay, let's continue. Part E. Let me use a different color P to distinguish. Okay, part E. So how many ways can 8 persons be arranged around a circular table? Oh, we already mentioned this before. If it's 8 persons, then it's 8 minus 1 factorial, right? And so how do we think of that? Okay, let's revisit again. So we have 8 persons. Step 1, we want to place a person. Okay, just pick any person and place it there. And we count the number as 1 because the different arrangement actually represent the same thing. Okay, we mentioned it before. So we count the number in this step is 1. Then the second step, we can place other persons. Okay, so we place other persons. That's why we have 7 factorial. Okay, because we have 7 persons left. And in this case, we also consider the counterclockwise direction and the clockwise direction. They are the different arrangements. Okay, so if you consider the counterclockwise direction and the clockwise direction represent the same arrangement, you're gonna divide your answer by 2. Okay, so this is just couple remark. Okay, so let me put down the remark here in a different color. Okay, so remark. Okay, so if you consider the clockwise and the counterclockwise directions the same arrangement, you need to divide our answer by 2. What I mean by consider clockwise direction and counterclockwise is the same arrangement. I mean, okay, 1, 2, 3, 4, 5. Okay, if you think this guy is the same as 1, 2, 3, 4, 5, right? Like clockwise and counterclockwise. If you think they are the same arrangement, then you need to divide it by 2. In our textbook and homework, and if I didn't say we consider the clockwise and counterclockwise as the same arrangements, I mean we think they are different arrangements. So far, so good, everybody. Okay, so here are some couple remarks. Okay, next. We call what we have done now. We already we've done a lot of examples with the order matters. But now, if we want to find the number of ways in which our objects can be selected from a set of n objects, but we don't care the order in which the selection is made, we call this sets of R objects as a combination. Okay, so we call that 4, 1, 2, 3 is a permutation. Okay, then the sets 1, 2, 3, 4 is a combination. Okay, we usually just put down the number or like the order pair to denote permutation, and we use sets to denote combination because the elements in the set, the order doesn't matter. So we can use set to denote combinations. Okay, so we know how to calculate permutations. Okay, but within those permutations, there are n permutations of any R objects. We select from a set of n distinct objects. Okay, so there are, if we don't care about the order, then there are R permutations represent the same arrangements. Okay, so permutation and choose R permutations of R objects contain each set of R objects R factorial times, such as the set of elements 1, 2, 3, 4, and we have 4 factorial permutation represent the same combinations. Okay, that's why for a set of R objects, we have R factorial permutations represent the same combination. Okay, so let's look at this. In how many ways can I select 3 people from a group of 3 people? Well, that is 1, right? Sorry, I pressed it. Let me make it bigger. Okay. That's 1. This is a set of 3 people, so only 1. Second, in how many ways can I select a group of 2 people from a group of 3 people? Wow. So what is it? First of all, you want to count the permutation. You want to count the permutations and choose R. So we have 3, choose 2. So how many permutations are there? So 3, 2, 1, right? And then the 2 people. So the two people we select, they represent the same arrangements. So that's why we have 2 in the denominator. 2 cancel. We have 3. Okay. All right, next. In how many ways can we select 5 people from a group of 10? Okay, first, what is the total number of permutation? 10 factorial. Okay, then within those permutations, for each set of 5 people, there are 5 factorial permutations represent the same thing. So that's why we divide it by 5 factorial. Okay, that's why in general, the number of combinations of R objects selected from a set of N objects, order does not matter, equals combination N choose R. There's another notation. We put the parentheses. Inside the parentheses, we have N and R. Be careful, don't put N and then a line, horizontal line R. This means fractions. Don't ever put the line there because it will mean fractions. Okay, and we usually use this notation. We use this notation a lot. So first, we want to count the total number of permutations. That's permutation N choose R. And then for each set of R objects, there are R factorial permutations represent the same sets. Okay, so that's why we divided by R factorial. Okay, and what is permutations N choose R? That's N times N minus 1 times times N minus R plus 1. So we start with N, we count down for R numbers, and then divide by R factorial. But the permutations also equals to N factorial over N minus R factorial. That's why the combination, you just have an extra R factorial in the bottom, at the bottom. Okay? All right. So let's continue. Example, how many ways can we pick 7 people, specifically 4 women and 3 men from a group of 10 women and 8 women? Okay, so here, step 1, we want to pick women. Oops. All right. Okay, so we want to pick women, and women, we have 10 women. We want to pick 4 women. So this is combination and 10 choose 4. Okay, this is the first step. We want to pick women. Okay, then the second step, let's pick the men. Okay, so we have 8 men and we pick 3 men. Okay, so what is this? How do we calculate? Okay, 10 choose 4 is, we start with 10 and then we count down 9, 8, 7 over 4 factorial. So 4, 3, 2, 1. Okay, this is 10 choose 4. 8 choose 3. 8, count down 3 numbers. 8, 7, 6 over 3 factorial. So 3, 2, 1. Okay, plot this in our calculator. We get 10 times 9 times 8 times 7 times 8 times 7 times 6 divided by 4 divided by 3 divided by 2 divided by 3 divided by 2. Our answer is 11760. Or before you plug in, you can do some cancellation. You can cancel the 4 and 2 and 8. You can cancel the 3, 2 and 6. And then it can save you some work before you plug in your calculator. So far, so good, everybody. Okay, I also want to put down some remark here. Okay, so what do I want to put down here? Okay, so here's some remark. N choose 0 equals N choose N equals 1. Okay, so if R is 0, you can see 0 factorial is defined to be 1. Okay, then you see, then you're gonna be N factorial over N factorial, that's 1. Okay, next, N choose 1 is N choose N minus 1. That equals N. Okay, when we plug in R is 1, this is 1, this is N minus 1 factorial. So that's why we just left with N. And actually, from this formula, we can see that N choose K equals n, choose n minus k for all k. See, if you plug in r to be n minus r, but then this guy just become r, this guy become n minus r. They just kind of switch. Okay, so far so good, everybody. Okay, so do you remember in the session 6.1 when we count the number of subsets of a set of n elements? There are second way we use combinations and the binomial theorems. So if you didn't understand at that time, you can now we have learned combination and how to compute combinations. You can go back to that example and play that video and kind of try to go through the problem again. Of course, if you have some questions, feel free to ask me in class or in the office hours. Okay, cheers. Next example, I would like to continue in video part B. So because it's gonna be an interesting example, and we'll do tons of calculation about that example. Okay, so let's continue in video part B. See you soon.